Beijing just finished a machine meant to end a 20-year gap in chip making. If you've seen the headline, that's about all you got. What got left out is that the machine fills nearly a whole factory floor, built from reverse-engineered second-hand parts in a high-security lab in Shenzhen. The machine it's chasing, an ASML scanner, is roughly the size of a school bus. This one needed a whole building. But size isn't the story. The story is what's missing inside and why the whole effort now hinges on a colorless gas Beijing just cut off. Now, to put that gap in perspective, for almost 2 decades, one company in the Netherlands has held a total monopoly on the machines that print the smallest, densest chips on Earth, ASML. Not Intel, not Samsung, not even NVIDIA, the company whose chips currently power most of the world's artificial intelligence. All of them, every single one, depend on machines built by one Dutch company because ASML is the only manufacturer on the planet that has ever gotten extreme ultraviolet lithography to work at commercial scale. Every processor in a modern smartphone, every advanced chip inside an AI data center, every cutting-edge chip going into a fighter jet or a missile guidance system, all of it eventually traces back to an ASML machine somewhere in the supply chain. A single company, in a single small country, sitting at the top of a global technology stack worth trillions of dollars, and until very recently, almost nobody outside the semiconductor industry had any idea that company's name. China has none of them. Since 2019, export controls out of the Netherlands, backed by pressure from Washington and Tokyo, have blocked the most advanced version of this technology from ever reaching a Chinese fab, the single choke point, holding back China's entire advanced chip industry, the one piece of the puzzle money alone can't buy, because the company that makes it is legally barred from selling it, no matter how large the check China writes. This is why the Shenzhen prototype isn't just a technical curiosity. Advanced chips are the actual currency of the AI race, and the AI race is the thing every government on Earth currently treats as a matter of national security, not just business. Taiwan's TSMC, sitting just off China's own coast, currently manufactures most of the world's most advanced chips using ASML tools that China can't legally buy. Every year China stays locked out of extreme ultraviolet lithography is another year its most advanced chip companies stay a generation or more behind the chips training the world's leading AI models. That's the real stake sitting behind this entire program, a bid to remove the one lever the rest of the world currently holds over China's entire technology industry. So Beijing did what Beijing tends to do when it hits a wall like that. It decided to build its own. In December of 2025, Reuters reported that a team including former ASML engineers had completed a prototype extreme ultraviolet lithography machine inside a high-security lab in Shenzhen. The machine was assembled largely from reverse-engineered and second-hand parts, and multiple outlets that picked up the report, including Power Electronics News and Tech Power Up, described the finished prototype as taking up nearly an entire factory floor. Notice the phrase, reverse-engineered and second-hand parts. That isn't how a company builds a machine when it can simply order the components. That phrase is what it looks like when a country can't legally buy the parts it needs and has to source them piece by piece anyway, through channels nobody involved is eager to detail publicly. High security isn't a throwaway detail either. A prototype this politically sensitive, built partly from components that were never supposed to leave their country of origin, doesn't sit behind normal factory doors, and every engineer who worked on it signed on knowing exactly what kind of program this actually is. Chinese sources cited in that same reporting put a realistic target of 2030 for the machine to start producing chips at commercial volume. Some state-linked Chinese reporting has floated an earlier date 2028 for a first working output. Either number puts this year's out, not months, and that gap between "we built a prototype" and "we can run a factory on it" is where this story actually lives. So what did they actually build if not a copy of ASML's machine? A different machine chasing the same result through a completely different route, and the differences start at the very core of how the thing generates light in the first place. ASML's production scanners create extreme ultraviolet light through something called laser-produced plasma. A carbon dioxide laser fires at 50,000 droplets of molten tin every single second, vaporizing each one into a plasma that emits the exact wavelength of light needed to etch features smaller than a virus onto a silicon wafer. Read that again. 50,000 precision hits on falling droplets of liquid metal every second without missing, for years at a time inside a working chip fab. It sounds almost impossible, and for years it basically was. ASML spent decades and tens of billions of dollars getting that process stable enough to run non-stop in a factory rather than a research lab. China's prototype doesn't attempt this. According to EE Times reporting from December of 2025, the Chinese machine uses a different method entirely, called laser-induced discharge plasma. Instead of a laser vaporizing a stream of falling tin droplets, two rotating electrodes coated in tin spin toward each other and a capacitor discharge, essentially a controlled electrical spark, blasts the tin into plasma at the point where the electrodes nearly touch. No droplet generator. No 50,000 precision hits a second. A mechanically simpler path to the same wavelength of light, built from a completely different set of engineering assumptions. Here is why that choice matters. ASML's droplet method produces a small, incredibly stable, incredibly bright point of light, over and over, with almost no variation from one pulse to the next. That stability is what lets a chip fab run the machine at full production speed for months without the pattern drifting off the wafer. The rotating electrode method. China is using sidesteps the near impossible precision of hitting 50,000 tiny falling droplets a second, and that's exactly why a team without ASML's decades of droplet engineering could actually build it. But simpler usually trades away something. Two metal electrodes physically eroding against each other, spark after spark, don't last nearly as long as a laser aimed at falling droplets that never touch a surface. Every discharge wears the electrode tips down a little further, which means the light output drifts over the life of the part instead of staying fixed, and a chip fab cannot tolerate a light source that quietly changes on it mid-production run. Less consistency, more wear, and light output that multiple outlets citing different sources put well below what ASML's commercial machines produce. China chose the version of this machine it could actually build with the parts and the talent it had access to. Whether that version can survive months of continuous factory use is the part nobody outside that Shenzhen lab has proven yet. And that engineering decision didn't come from nowhere. It traces back to specific people, recruited on purpose, and the story behind them is more complicated than most coverage has made it sound. Leading part of the light source effort is Lin Nan, who once ran light source technology for ASML itself, before returning to China in 2021 through the country's National Overseas Talent Recruitment Program, the same pipeline Beijing has used for years to pull scientists and engineers back from Western companies and universities. His team, based at the Shanghai Institute of Optics and Fine Mechanics, published research in the China Laser Journal in March of 2025, outlining a solid-state laser approach to generating the light, and the South China Morning Post covered that research that May. That's one track, and it's the one most headlines have latched onto, because the man who ran ASML's light source division just built China's version is a clean, simple story. But here's the part most coverage of this skips entirely. The rotating electrode method, the laser-induced discharge plasma design actually built into the Shenzhen prototype, is credited in other reporting to a separate team at Harbin Institute of Technology, working an entirely different physical approach to the exact same problem. Two institutions, two different engineering bets, running in parallel, not in sequence, and not necessarily talking to each other in lockstep. This isn't one defector single-handedly solving China's lithography problem, the way a lot of the coverage has framed it. It's closer to a country funding multiple competing paths at once, betting that at least one of them eventually scales because nobody in Beijing knows yet which approach, the solid-state laser or the spinning electrode, actually wins. That's a messier, more expensive story than one genius comes home and fixes everything. It's also probably the more accurate one, and it says something about how seriously this is being taken, that Beijing is willing to fund two separate institutions chasing the same finish line instead of picking a single horse and betting the whole program on it. It's worth sitting with why that framing matters beyond just getting the facts right. If the story really were one engineer defecting and single-handedly cracking a problem ASML spent 20 years on, that would suggest China's breakthrough depends on a handful of irreplaceable people, and losing any one of them sets the whole program back years. Two institutions running two different physical approaches tells a different story. It tells you Beijing isn't betting the program on any single person's expertise. It's treating the light source problem the way a venture fund treats an uncertain market, by funding competing approaches and letting the results decide which one survives. That's a more resilient strategy than the lone genius headline suggests, and a more expensive one, which is exactly why most short news write-ups skip it in favor of the cleaner story, because generating the light is only the first problem this machine has to solve. Getting that light to actually etch a working chip is the next one, and it might be the harder one. Extreme ultraviolet light gets absorbed by almost everything, including regular air and regular glass lenses. That's the reason ASML's machines don't use lenses at all past the light source. They use a chain of mirrors instead, mirrors polished to a smoothness measured in individual atoms, sitting inside a near-total vacuum, because a single stray molecule of the wrong gas in the wrong place can scatter the light before it ever reaches the wafer. Building mirrors that precise, and keeping that chamber clean enough to matter, took ASML the better part of 2 decades working with a tiny handful of specialist optics suppliers based in Germany, companies that essentially have no real competitors because almost nobody else on Earth has ever needed to solve this specific problem. There is no public reporting confirming China's prototype has matched that piece yet. The light source is the part getting the headlines right now, because it's the part reporters could get details on. A spinning electrode and a spark are at least a story you can describe in a paragraph. Mirrors polished flat to within a fraction of a single atom aren't the kind of detail that leaks out of a facility this locked down, and neither is the exact purity of the vacuum sealing them in. The vacuum system and mirror chain sitting behind the light source, the part that actually determines whether this machine can print a usable chip pattern rather than a smear of scattered light across the wafer, is the part nobody outside that Shenzhen lab has shown working at production quality. You can build a bright light. Making that light do useful work on a wafer is an entirely separate engineering problem, and it's the one ASML's German optics partners spent 20 years quietly solving while nobody was watching. If you're finding this breakdown useful, subscribe. This channel covers the technology racing to reshape global power every single week, and this prototype sitting in that Shenzhen lab right now is one of the biggest bets running anywhere on Earth. And running a vacuum system this sensitive, keeping the whole chamber stable and free of contamination for a process this fragile, depends on one specific, almost boring input that has nothing to do with lasers or mirrors at all. Helium. Helium is chemically almost inert. It doesn't react with the materials around it, and that's exactly why chip fabs and lithography tools lean on it to purge and cool machinery without contaminating a process this sensitive to interference. There is no real substitute. You can't swap in a cheaper gas and expect the same result, because the whole reason helium gets used is that nothing else behaves the same way at this level of precision. And China has a helium problem that has nothing to do with engineering talent and everything to do with geography, because helium doesn't exist in extractable quantities almost anywhere on the planet. China imports more than 85% of what it uses, according to reporting from Trivium China and TrendForce in mid-2026. More than half of those imports have historically come from a single country, Qatar, with Russia supplying most of the rest. Then, on July 10th of 2026, China's own Ministry of Commerce imposed an immediate, open-ended ban on helium exports, citing the need to protect domestic supply. Sit with that for a second. This isn't a problem ASML or the Netherlands created. Beijing just cut off its own factories from a gas its own chip industry can't function without. The ban followed a string of supply shocks earlier in the year. Iranian strikes had knocked Qatar's Ras Laffan facility, one of the largest helium sources on the planet, offline entirely. Russia, the other major supplier feeding Chinese demand, had already tightened its own export controls back in April. So by July, China was staring down a shrinking supply of a gas it barely produces domestically, watching 2 of its 3 major foreign sources get squeezed within months of each other. And the response wasn't to scramble for a new supplier somewhere else in the world, the kind of move a country makes when it still believes the shortage is temporary. It was to lock down what little domestic supply remains and hope the shortfall never reaches the machines, meant to close a 20-year technology gap. Think about what that actually means for a program this ambitious. You can reverse engineer a light source, given enough time and enough recruited engineers. You can pull the exact people who used to build the real thing back across the world through a talent program. You can't recruit your way out of a gas that only a handful of countries on Earth can extract in useful volume, and you can't ban your way into having more of it either. Recruiting solves a knowledge problem. This is a geology problem, and geology does not respond to a national talent program the way a physics equation does. A helium shortage doesn't care how good your optics team is, or how many patents your rotating electrode design holds. It just runs out. And this is exactly why buying the finished ASML machine was never actually on the table, even before the export controls existed. A lithography machine like this isn't a single product you purchase once and run forever. It's a living supply chain. Mirrors from Germany, control software patched constantly from the Netherlands, service technicians flown in for anything that breaks, and gas inputs sourced globally. Export controls don't just block the sale of the machine itself. They block the entire support relationship a machine like this needs to keep running for a decade. Even if China somehow acquired one working ASML scanner tomorrow, it would still need a functioning helium supply chain to run it, the exact supply chain currently tightening around China's own domestic prototype. Building the machine from scratch was never really a choice between two options. It was the only path left once the first one closed, and everything downstream of that decision, the electrodes, the mirrors, the helium, is China now having to rebuild an entire supporting industry that took the rest of the world decades to assemble, all at once, under sanction. So where does all of this actually leave the machine right now in 2026? China's leading chipmaker, SMIC, is already producing chips at close to the 5-nanometer class, the tier of chip that used to require extreme ultraviolet light to manufacture without any EUV machine at all. According to reporting from Power Electronics News in February of 2026, SMIC does it by running its existing deep ultraviolet tools through the same silicon wafer 4 separate times, quadruple patterning, layering pattern on top of pattern until the final result approximates what a single EUV pass would deliver in one step. Picture tracing the same complex drawing 4 separate times on the same page, each pass adding detail the last one couldn't capture alone, and every single pass has to line up with the last one within a margin smaller than a virus or the whole chip is scrapped. It works. It has been working for years now. It's also slower, it burns through far more materials and process time per chip, and it produces a lower percentage of usable chips off every batch, because every extra pass through the machine is one more chance for something to go wrong on the wafer. SMIC has been running that workaround specifically because, until now, it has had no other option, and every chip that comes off that line costs more to make and takes longer to produce than the same chip would if a working EUV machine did the job in a single pass. Multiply that extra cost and extra time across every advanced chip China's entire domestic industry currently needs, and the size of the prize sitting behind that Shenzhen prototype starts to come into focus. That's the real weight sitting on top of the Shenzhen prototype. If this machine works, and works at real sustained production volume, China stops needing the 4-pass workaround entirely, and the yield gap and the cost gap separating it from the rest of the global chip industry start closing fast, with consequences that reach well past China's own borders, into every supply chain that currently assumes Beijing stays a step behind. If it doesn't, if the electrodes wear out faster than a production line can tolerate, if the helium supply keeps tightening instead of stabilizing, if the vacuum system behind that light source never reaches anywhere close to the precision ASML spent 20 years perfecting, SMIC keeps running 4 passes through machines built for an earlier generation of chip, and the gap holds where it already sits. Chinese sources are already pointing to 2030 as the realistic year to find out which future actually happens. Some state-linked reporting says 2028. Nobody serious inside this program is calling it solved today in 2026, and the people funding it know that better than anyone watching from outside. What China actually built is a bet, split across 2 institutions. One recruited defectors' light source design, and one increasingly fragile imported helium supply chain, betting that a cruder version of ASML's idea can eventually be made to work at real scale. Whether that bet pays off before 2030 depends on a rotating electrode surviving months of factory conditions, a mirror chain nobody outside Shenzhen has actually verified, and a gas Beijing just decided to stop selling to anyone, including, it turns out, itself. That's the machine sitting in that factory floor tonight, still years from proving it can do the one thing it was built to do. Every subsystem inside it, the light, the optics, the vacuum, the gas that keeps all of it stable, has to work at once for months on end before this counts as anything more than a very expensive proof of concept. Whether it ever actually closes the gap with ASML is still an open question. And the answer to how China even ended up 20 years behind on this technology in the first place, and who actually solved the piece China still can't, that story is sitting in the video on screen right now.